Hello, everybody. Welcome to our next seminar. Today, it is my pleasure to announce Professor Hanna Zbroszczyk from the Warsaw University of Technology, from the Nuclear Physics Division. Professor Zbroszczyk is an experimental physicist who specializes in heavy ion collisions at high energies. She's a long-standing member of the STAR collaboration at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory. So with hundreds of publications and tens of thousands of citations, she's one of the leading experts in nuclear physics worldwide. So please join me in welcoming Professor Zbroszczyk.
So first of all, very warm good afternoon, ladies and gentlemen. It is my big pleasure today to discuss results that we received with our collaborators from the STAR experiment related to first evidence of the antimatter hypernucleus. And of course, I'm very grateful for this very kind invitation. I'm very happy to be here today. So here you may see an outline of today's seminar. So I expect I will speak about quite exotic topic for you. That's why I prepared quite extended introduction. So I would like to briefly discuss hypernuclei and also some topics related to our research domain. So very quickly we also go through the universe, through time, also finding where the problem of antimatter exists. Then I will jump to the area which is very closely related to my everyday researches, like exploration of QCD phase diagram that describes strongly interacting matter. Then, of course, I will say a few words about the experimental facility, introducing experiment that perform this exciting measurement and discovery. And then the main part will be related to antimatter particles that we discovered. And also I will tell you more details about what we have found and what we can learn from this studies. So let me start with hypernuclei. And if we check what hypernucleus is, even if we take into account what we find even in Wikipedia, you may see that hypernucleus is a kind of object that is compared to atomic nucleus. However, as we know very well, atomic nucleus is composed of nucleons, protons, and neutrons. And speaking about hypernuclei, we have in mind that instead of at least one nucleus, instead of one proton or neutron, we substitute it by hyperon. And I will tell you about these objects and what's the experimental status related to this area. But also I would like to mention that we can really be proud because the first hypernuclei were discovered by our Polish researchers. And this discovery took place in 1952 by Marian Danysz and Jerzy Pniewski from University of Warsaw. And so the first hypernucleus was discovered in September 1952 by these two gentlemen. That took place in University of Warsaw. And since then, of course, era of new fascinating discoveries started. And also I would like to mention that just 5 years before, V particles were discovered just in 1937. So V particles are particles that decay due to that decay weakly, like for example lambdas or neutral kaons. And at that time, when there was a lot of interest regarding V particles, these two gentlemen observed signals that the first impression was that was something surprising. And they expected that signal they saw probably was related to these V particles. However, after deeper investigation, it came out that that was a signature of completely different object that was hypernucleus. And now I would like to briefly mention the most elementary blocks of matter, because if we speak about the most fundamental constituents of matter, so if we take protons, if we take neutrons, we know they are made up quarks. And speaking about quarks, we have 6 different flavors. And we have up and down and charm and strange and top and bottom. And only if we take into account quarks of the first generation, up and down, these quarks are responsible for our how protons and neutrons are made up. So if we take into account, here you may see example, proton and neutron. So proton consists of 2 up and 1 down quark, neutron 2 down and 1 up quark. However, we also keep in mind that except these 2 flavors, we have 4 others: charm, strange, top, and bottom. And then if we take into account the third light quark, which is strange one, then what was discovered in years that particles containing the strange quarks, they decay due to weak interaction. And here I would like to mention the lightest possible baryonic hyperon, which is lambda particle. And lambda consists of 1 up, 1 down, and 1 strange quark. So if we speak about nuclei, we obviously understand that they are composed of protons and neutrons only. However, if we substitute at least one of these nucleons by hyperon, lambda hyperon, for example, then we obtain object that we called hypernucleus. And so this is about the matter example of hypernuclei. And before we move forward, I would like to also mention why hypernuclei are important. Because of course that was very important discovery. However, from the point of view of researches that we conduct even today, so recently more and more interest is directed into neutron star. And this is because of we expect that neutron stars are quite dense, small, compact, but dense object. And from observation, we expect the mass of neutron star to be between 1.5 and let's say 2 solar masses. However, everything depends which constituents we take into account thinking about neutron star. And this brings me to a topic which is quite relevant, especially recently in our community, where we ask a question about equation of state that describes neutron stars. And here we really deal with a problem. What really builds neutron star? Because depending on whether we consist purely matter made of neutrons or whether we include also composition of hyperons, we get various equations of states. And of course, taking into account these various equations of state, we end up with different calculations related to mass of neutron stars. And because from observation, we expect a mass of somewhere between this orders of magnitude. However, we also understand that taking into account conversion from nucleus to, for example, lambda hyperon. So it means that we rather would expect such kind of equation of state. And here we really comes to something that we call neutron star puzzle, because if we take into account inclusion of hyperons inside neutron stars, it means that the mass of neutron stars does not match what we expect. And here, for example, in order to understand on one hand how we can really consider inclusion of those inside neutron stars, we enter the problem of interaction. And this is another topic that is really intensively studied in our group, for example, related to interactions between, for example, nucleons and lambdas and so on, in order to understand better equation of state. So here I would like to really mention that hypernuclei are really essential in order to learn about possible equation of state that describes neutron stars. And here we have several questions that are also quite important in our domain. So like, for example, how nuclei and hypernuclei are formed, what are their characteristics, and also very important for our group, how to describe interactions between nucleus and between hyperons. So the problem of equation of state is understood as really important for a long, long time ago, and now we also put a lot of effort in order moving forward these topics. So, so that was about hypernuclei. Should we ask questions now, or in the end, I don't know? Okay. So, okay, now I would like to touch a bit the problem of universe. And this, I believe you are familiar more or less. However, so if we take into account universe evolution, so everything started quite long time ago, about 13.7 billion years ago, and we had a moment of Big Bang. And then we distinguish between various stages of this evolution. And first we had very rapid evolution. We had inflation, and here you may see how formation of matter evolved in years. Also, you may see some time scales. So, first of all, this time interval is absolutely not possible by us to study. And here we enter area that is potentially observable, and but this is related to formation of first galaxies and stars. And this is a time interval about few hundred millions after the Big Bang. Then, of course, we have evolution, expansion of the universe. Here we have the moment when everything started to accelerate, formation of solar system. Here we have the first forms of life. Here we are today. And I would like to focus on this area because the moment of Big Bang, how we understand this, we don't know why. However, the matter that creates the universe today was just located in one point. So starting from this moment, we expect from the most elementary constituents of matter how they build the universe observed today. And here we have very interesting regions starting from the most constituent forms of matter like quarks, like gluons, like leptons, and so on. And here you may see, for example, that we have first particle reactions, first nuclei form, first atoms, and so on. And now the question is, can we really somehow access this very interesting, however, absolutely not possible to study area? And here I would like to pay your attention. This is the same picture, however, in quite different illustration, because here shortly after Big Bang, what is really important to mention that what we expect that at the moment at the initial moment, we expected the same amounts of matter and antimatter. And we don't know why. However, during time evolution, this matter and antimatter particles annihilate with each other. Starting from this area, we observe only universe made of matter. And this is really puzzling because we don't know why. However, for some reason, the antimatter disappear. And of course, at this moment, we are not able to answer the question what really happened to antimatter. However, our efforts go in two directions. First of all, trying to understand the properties of the most elementary antimatter particles. And then, if we really confirm that we have symmetry between matter and antimatter, we can go further and try to answer following questions. So, speaking about antimatter, here you may see the most elementary example of matter. So this is hydrogen atom, just one proton inside and one electron. Proton consists of up and down, two up and one down quarks. And here we can also discuss also one of the most elementary example of antimatter, which is anti-hydrogen atom consisting of one antiproton and one positron. And here we see that if we speak about antiproton, so proton is made up of quarks, antiproton is made up of antiquarks, and we have symmetry, like we have two anti-up quarks and one anti-d quark. So here you may see that we have the most elementary constituent of quarks, 6 flavors, up, down, charm, strange, top, and bottom, together with leptons. And also, on the other hand, we have blocks of antimatter like antiquarks. So antiquarks, again, up and down, and charm and strange, top and bottom. And these are the most elementary examples of particles. And now how they can build matter. So there are limited possible ways how they can build particles. So if you, for example, build a particle of up to 3 quarks, so such examples we call baryons, and we have proton, we have neutron, we can also discuss other possible combinations. We can also build particles from antiquarks, like antiprotons, antineutron, and so on. And also we can build particles from quarks and antiquarks, and here we have mesons, like pi plus, chi zero, and so on, so on. So these are possible examples of how quarks can build matter. So, okay, so now I would like to briefly introduce how we experimental physicists with our tools like heavy ion collisions, how we can answer these questions that I mentioned. And I would like to start with phase diagram. And this is the phase diagram of water that you know very well, of course. So we have phase diagram in physical chemistry, engineering, mineralogy, and material sciences that exhibit conditions of phases coexisting at the stage of equilibrium. Here we have a diagram shown in variables like pressure and temperature. And speaking about this phase diagram, we of course understand different phases, and these multiple phases coexist together, and also we have phase transition along these phase boundaries. And here we discuss QCD phase diagram. This is quantum chromodynamics phase diagram, in other words, diagram of strongly interacting matter. And here you may see some similarities. So we also have temperature, and instead of pressure, we rather deal with the quantity which we call net baryon density. This is baryonic chemical potential. However, also you may see various two stages. So here, for example, we have matter, quarks that are confined into hadrons, and here we have state that we call quark-gluon plasma. This is state where quarks and gluon exist in the state of equilibrium, but they are not bind together. And now we can realize various experiments taking into account collisions of various elements at various energies. And with these conditions, we can explore this QCD phase diagram. And so, for example, if we consider the highest possible energies like those achieved at LHC at CERN, here we are able in the laboratory recreate conditions similar to those existing shortly after Big Bang. And then if we consider a little bit lower collision energies, then we enter this area, also very interesting, because here we have very characteristic structure. So here you may see a line of transition between hadronic and quark matter, and here you may see very interesting behavior. So if we take into account relatively high temperatures and relatively low net baryon density, here we expect a transition between hadronic and quark matter that we call a crossover transition. However, here we rather expect a transition of the first order. And somewhere here we expect a point that we call critical point. This is very important point in our community. First of all, many experiments really hunt on this point for many, many years, so far unsuccessfully. However, this is also the region that gains a lot of attention, especially recently, also by our experiment. And here, if we decrease, again, collision energy, then we enter another fascinating region of this QCD phase diagram. And here you may see that here we put conditions that are expected to exist, for example, in neutron stars or neutron star mergers. So, so the point is that we can really steer the energy of the collision of heavy ions, and then depending on, of course, what we collide and which energy, we can study these various stages or various areas of QCD phase diagram. And I can really say that at this moment, the most recognized and the most understood region is related here, but everything what is here is really under very strong consideration right now. Okay, so here is the status of what we know regarding exploration of QCD phase diagram. So, as I mentioned, this region, which describes conditions of early universe, here we expect so-called crossover transition between hadronic and quark matter, somewhere here we really don't know where, but we expect the critical point. And the idea was to decrease the energy of collided nuclei in order to find possible signatures indicating location of this critical point. However, this location changes, so there are many, many efforts together with our theory colleagues in order to find location, but I can already tell you that there are so many predictions that even now we have the region where we expect, but these regions, of course, changes while we obtain another results of experiments. So here the point is that if we enter high baryonic potential and relatively low temperatures, here we really enter unknown phase structure. And we really don't know whether there is a first transition of first order, whether there is critical point, whether we have some mixed phases, new phases. There are really still a lot of challenges related to properties of matter to determine, related to description of hadrons, equation of state, and of course neutron stars. So now a bit about tool that we use. We use collision of heavy ions. And here you may see example of gold-gold collisions at 200 GeV. This is relatively high collision. And the point is that with collisions of heavy ions, we are at some point able to reproduce conditions existing to those that we expect existed shortly after Big Bang. So at some point we realize in laboratory conditions small Big Bang, and the main goal is to reproduce these conditions in order to be able to study conditions that we believed existed shortly after Big Bang. So that was the main motivation. And more than 20 years ago, the main motivation was to discover QGP phase. So this phase where we have deconfined matter, quarks and gluons, because we expected that this phase should have existed shortly after Big Bang. However, we needed experimental evidence, and that really happened. Because if we collide heavy ions, relatively high energies, it is indeed possible to recreate conditions when we register this state. And I'm very proud that experiment to take part, the STAR experiment was experiment that registered the state for the first time. So here we are also possible to recreate conditions where we observe annihilation of matter and antimatter. And this happens somewhere here at the beginning of this evolution. And the point is that what we observe in the experiment is related to these final stages of particles. So imagine that we collide heavy ions like gold or lead or any other example. So heavy ions are made up of protons and neutrons. And then because we have really huge energy and quarks and gluons are deconfined, energy is large enough in order to create other quarks, other matter, and then you may see evolution of the system where in the final stages we have various particles. So what we really observe in experiment are these various particles, and we can analyze their properties in order to learn what really happens somewhere here. So this is the moment where we have expected also creation of antimatter. So heavy ions are really effective tool in order to create and study antimatter, nuclei, and hypernuclei. And here I would like to briefly mention STAR experiment. So STAR experiment is located at Relativistic Heavy Ion Collider. This is experimental facility, and this year we collected data for the last time after 26 years of operations. So the facility consists of 2 rings with circumference of almost 4 kilometers. We have 2 independent rings, and at the points of these interactions we had detectors, and we observed collisions of various systems. And here you may see how many various systems we analyzed in years. So the highest possible energy we achieved was, in case of collision of protons, up to 510 GeV per proton pair, and 200 GeV per nucleon pair in case of gold-gold nuclei. So speaking about STAR experiment, STAR is only one experiment taking into account many various projects, and STAR experiment operated with various collision energies in order to study really wide area of the QCD phase diagram. And here you may see collection of how many data we collected in years, how many systems, how many energies. And with this very huge collection of data, we are able to study really various possible characteristics. So we perform beam energy scan of this phase diagram in order to study possible phase transitions. We study system dependence as a function of this energy. We discovered many fascinating properties. And also one of our interests was also to look deeper into production of antimatter, and in a moment I will tell you what we have found. So I would also like to mention that the way how we work, we identify particles. And from experimental point of view, what we can do, we can, for example, in detector measure the energy loss per length unit for various particles. And if we measure these properties, we are able to distinguish between various particles. So it's also challenging because you may see that how many these trends overlap. So very often we need information from various detectors in order to identify particles with the highest possible purity of this. And here you may see characteristic trends. So this is how we recognize particles. However, in this way, we can recognize only so-called primordial particles. So if we deal with particles that decay, so then we are able to distinguish rather decays of products, and then taking into account that we know topology of the particle decay, we can reconstruct the original particle. So speaking about major discovery, so I think the main idea of this analysis was was not very complicated, because the main idea was related to find particles that could form this form of the heavier possible anti-hypernucleus. And successfully this was achieved, and this result also was published in Nature. It gains a lot of attention. And here you may see constituent particles that are inside this hypernucleus. So if we speak about anti-H4 lambda, it means we have particles which have one antiproton, two anti-neutrons, and one anti-lambda particles. And here you may see how various examples of antimatter particles were done in years. So in 1925, Paul Dirac found possible solution with positive and negative energies in his equation. So that was the first idea related to possible antimatter particle. And this negative energy solution indicates new particle with the same mass as electron, but with opposite charge. And in 1932, Carl Anderson discovered in cosmic ray new particle that is positron. So we are here. And since then, theoretical framework for the experimental foundation for the study of antimatter was established. And here you may see that in years, heavier and heavier examples of antimatter were discovered. So here we have the first register antiproton, anti-neutron, anti-lambda, anti-deuteron, anti-helium-3, anti-triton, anti-helium-3, anti-helium-4, and here finally we have our discovery. So if we speak about how we recognize signatures of anti-H4 lambda, so first of all, we need to understand what are decay products of this particle. So here you may see that if we speak about anti-H4 lambda, the decay products are anti-helium-4 and positive pion. And here you may see very similar example for H4 lambda for matter particle. And also taking into account the studies, we were of course focused on finding evidence for anti-H4 lambda, but of course making sure that we really discovered these particles. We actually repeated other analyses in order to verify whether we can also confirm our previous discoveries related to other particles. So the point was that to identify decay products like helium-4, negative pions in case of H4 lambda, and anti-helium-4 and positive pions. And these are particles that we identify through so-called energy loss technique. So we combine information from two detectors in order to make sure that we really see these particles that we expect to see. And I would like to mention that in total, 6.4 billion various collisions of heavy ions, including uranium, gold, isobars, ruthenium, and zirconium were analyzed. And in a moment, I will tell you how many examples we have found. So the point is that once anti-hypernuclei or hypernuclei is created, they fly only a few centimeters, then they decay. So then we reconstruct their decay products, and we really need to make sure that what we measure really origins from this particle that we look for. And here you may see examples. So this is, you may see how many helium-4 we register and how many anti-helium-4 we register. So taking into account these impressive statistics, really not so many of them. And you may ask, for example, how it's possible that we know that we take two particles and we connect them and we really know that it comes from this particle of our interest. So we use a quantity that we called mass, invariant mass, and this is the equation that we use. So the point is that having decayed products, we are able to calculate the quantity and we can find whether these two particles are really candidates of particle of our interest. And here you may see we took many pairs of particles, including helium, including pions. We constructed these pairs in order to, and we find such distribution. And of course we take into account that we also measure background. That's why we used several experimental techniques, understanding how pure background distribution look like, and this is what you can see. So the evidence of the signal really is related here. If we take into account signal and background, if we subtract these two, this is what you find, and you may see that having such impressive statistics of heavy ion collisions, we have calculated in total 24 candidates of helium H for lambda and 15.6 candidates for H, anti-H for lambda. So this is really the result. That we obtained, and we calculated significances levels and so on in order to see how much we vary from just pure background distribution. However, the signal is quite prominent. So speaking about possible matter and antimatter, once we register these particles, then we could take closer look into some properties. So according to, for example, CPT theorem, we expect the same properties for matter and antimatter particles. That's why our motivation was to compare properties like the masses, lifetimes, taking into account particles and antiparticles in order to find possible verification or lack of evidence for this verification for matter and antimatter asymmetry in universe. And here you may see we calculated these distributions that were used in order to determine lifetimes of our particles. And of course, the same time we studied not only our particles of interest, but all of them, like hypertriton, anti-hypertriton, H for lambda, anti-H for lambda. And here, so first of all, speaking about particles that we already knew from previous studies, of course, we confirmed our previous findings. And here we determine on also lifetime for our new exotic particle. And then we calculated lifetime differences in order to verify whether we get a number consistent with zero. And you may see that in, of course, uncertainties, these numbers are close to zero, which gives us this proof that we don't have actually reasons to think that they would be different. So our goal was to learn about production mechanism in heavy ion collisions. And also, so once we registered this example of particles, we also wanted to verify their possible production mechanisms. So, for example, one of the questions were whether this hypernuclei or anti-hypernuclei were directly produced as a result of this collision, or whether we rather should consider example of coalescence, like we had independent particles, and through systems evolution they formed the final particles. And here we also have tools how to study various product particles mechanisms. And we have some models, thermal models that assume thermal production, which means that these particles are considered produced directly as a result of this collision, and predictions of thermal models are indicated by these symbols. And of course, here we also put results of our findings. And this is really fascinating because for some particles in our experiments, of course, we find out that some of them are produced directly, but also many of them are produced as a result of coalescence. And here we also verify the scenario of coalescence, trying to predict possible particle ratios in order to verify possible coalescence scenario. And here was what we expected if we speak about coalescence scenario. So we actually compared these fractions, and based on our numbers that we calculated, we see evidence that we rather tend to scenario that these hypernuclei and antihypernuclei are produced as a result of coalescence. So these are the most important findings from our studies. So what I wanted to discuss and show you today that we registered first evidence of antimatter hypernucleus, which is H4 lambda. This is the heaviest possible antihypernuclei. Just, I think, 1 year later, one of LHC experiments discovered H4 helium, however, slightly lighter. So this discovery was done with our collaborators from the STAR experiment, and in total we managed to register 15.6 candidates, taking into account really impressive statistics of data that we analyzed. And so not only we managed to register these candidates, we also verified their lifetimes, and we tested the symmetry between matter and antimatter, not seeing really evidence why they would be different. And again, also what we wanted to verify was possible production mechanism taking into account various ratios. And this brings me to the final slide of my seminar. And the spokesperson of our collaboration said in one of interviews that it's only by chance that you have these 4 constituent particles emerging from Rig collisions that are close enough together that they combine in order to form this exotic anti-hypernucleus. And with this, I would like to thank you for your attention.
So now we have some time for questions. So let's maybe start with the Zoom audience. Do we have some questions from? Okay, so let's proceed with the on-site audience.
Thank you very much for a nice lecture. I have a question of a complete layman concerning this asymmetry between matter and antimatter in the universe. I always hear that it's a big problem, how to explain it. So first question is, at which, on this time scale you've shown us, at which stage it is already somehow visible or proved that at this moment there was this anti-symmetry? So, because I understand that at the very beginning it could have been so that the number of particles and antiparticles is more or less the same. So at which stage it happened, actually?
Are you asking about, can I go back to slide?
Yes.
Okay, so I guess, let me, no.
It was at the very beginning, I think.
Are you asking?
This is not so important. Okay, at some stage it is already somehow visible or proved that it was at this stage there was this anti-symmetry.
So at the moment of, if we speak about what we see in the experiment, so as a result of this collision, of course, we have excess of matter, right? Because we have protons and neutrons. So already we have excess of matter.
Okay, so at the beginning, when the universe was formed, there is no, I would say, proof that it was already at that time when it was.
Yes, so what we expect is that at the moment of Big Bang, the amount of matter and antimatter was similar. We don't have...
Okay, so I think that there is a very simple model how to understand this. So I can imagine that because they... Let's consider a mixture of two species, okay? Matter and antimatter, with more or less the same number of constituents of both, okay? Approximately, okay? So I can, because they annihilate when they collide, so it is very easy to write some kind of rate equations which somehow count or estimate or describe the rate of decrease of numbers of both species, okay? Which should be proportional, more or less, to the this right-hand side of this rate equation should be proportional to the product of densities or of numbers of these particles, because they have to meet one another. So such a system is, I believe, very unstable, and it has two or three maybe stationary solutions. So one wins, the second wins, or they annihilate each other and there is nothing, okay? So there is a very simple mechanism. So why we should look for something else? I understand that it could be disproved that something like that happened because, for example, during the annihilation, I understand that some photons are produced or some energies, okay? So for example, we do not see an excess of photons or something like this, which would exclude such a model. But what are the arguments to exclude such a very simple model? Yes, so at the very beginning it was, okay, more or less the same. Maybe there was a little bit more antimatter because of, yes, everything is...
But we don't know this. We don't know how, I mean, what we expect that at the moment of Big Bang, we had the same amounts of matter and antimatter. And for some reason...
up to one particle?
And
this is very improbable.
However, our
there is one direction, it immediately will be turned into production of the other side. You have to...
So in this model which I propose, there is no, okay, it could be in thermal equilibrium. There is approximately the same number of this and that, and they annihilate, okay?
But for some reason, the...
we know what was the excess of matter over the antimatter.
There should be some excess of matter of antimatter, just, okay.
Why there was such a...
Yes,
why?
But we don't know this. And to answer this question, why, we are not ready to answer. What we wanna understand, whether we can really verify that matter and antimatter examples have similar properties. And this is the level of our understanding at this moment. And to answer further question, I think it's still a lot of to do in order to understand it better. At this moment, we just wanna confirm whether we really see or whether we don't see a symmetry or asymmetry between matter and antimatter. And taking into account precision that is given by our experiments, where we are able to recreate experimentally conditions where we can fully control, and we see that if we deal with collisions of the highest possible energies, then we enter region of mu b0, where if we count these ratios of particles, we see symmetry between multiplicities of particles and antiparticles. Then if we go to region which is described by higher baryon chemical potential not equal to 0, then we see that these ratios are not really equal to each other because we have non-zero baryon chemical potential. But the point is that from the experimental point of view, we are able to recreate conditions. This is what is done at LHC. We are able to recreate conditions where we measure the same amounts of matter and antimatter. So at this point, we believe that with the best precision we have available on our planet, we can recreate at some point conditions similar to those existing shortly after Big Bang. And this is the motivation of our studies.
So we still have time for one quick question.
So excuse my rudimentary knowledge about the standard model and the quantum chromodynamics, but as far as I remember, it's about the CP still a bit. Mm-hmm. So standard model predicts very small CP asymmetry for hyperions because mesons are the main channels for us for the CP, I think, asymmetry.
The basic standard model?
Yes.
Or any of the improvements?
No, just the basic one. So I'm more or less familiar that there are this, dark interactions or double Higgs things.
It's not within the standard model. The basic
yes, I know,
standard model has so many questions.
But they predict, I think, CP asymmetry much larger in Hyperion. So do you think you can ever reach precision of your lifetimes of your measurements that we can actually distinguish between standard model and some of these extensions?
This is a very good question. And with currently available experimental facilities, I think it's impossible. However, there are ideas, inceptions, and there are some plans to build bigger machineries that would be able to explore and to verify also this further versions of not the most elementary version of standard model.
So we need more energy, basically.
Yeah. And also, so nowadays we also discuss more and more about possible dark matter and so on. So this is the area which is at this moment completely beyond our control. But in order to really understand the universe and all mysteries, we cannot fix only on matter because it's just a small fraction of the total universe. So there are many questions. So of course, we are not able to answer all questions. We want to just pick, one of these and to see whether we understand at least the small fraction.
Sounds like a good strategy to me. Thank you.
Yes.
Okay, so we can continue discussions at the coffee room upstairs. And for now, let's thank the speaker again.